Most renewable energy experiments fail not because kids lack curiosity, but because families buy a solar panel and a motor, then realize they have no way to measure what's actually happening. No data, no variables, just a spinning blade and a shrug. My name is Lakshmi Venkataraman, and I've spent years watching students transform vague demonstrations into rigorous investigations, and it always comes down to having the right supplies organized before you start. You're listening to the STEM Lab podcast. Quick heads up before we get going. Everything you're about to hear is researched, written, and verified by real educators and subject matter experts. That part's 100% human. The voice reading it to you, though, that's AI generated, which lets us get these episodes to you faster and more consistently. Anyway, if you've been with us for a while, thank you for letting us be part of your routine. And if you're brand new here, welcome. I think you're going to find this useful. New episodes come out every Monday, Wednesday, and Friday, so you've always got something to listen to on your commute or your morning walk. Let's jump into renewable energy supplies and exactly what you need to set your student up for real success. When you're gearing up for a renewable energy science experiment, you need more than curiosity and a workbench. You need the right supplies to turn abstract concepts like photovoltaic conversion and mechanical energy transfer into something your child can measure, troubleshoot, and genuinely understand. This walkthrough covers every category of supplies you'll need, from the core energy generation components to the measurement tools that transform a demonstration into a rigorous investigation. I've organized this based on how I scaffold these experiments in my own classroom, starting with foundational equipment and building toward advanced analysis tools that prepare students for genuine engineering problem solving. Let's start with core energy generation components. These are the workhorses of your setup, the components that actually capture and convert energy. You're not just buying materials here, you're investing in the physical representations of engineering principles your child will reference for years. Small photovoltaic solar panels in the 1 to 6 volt output range let students manipulate variables like angle, distance from light source, and surface coverage to observe real-time voltage changes. This builds understanding around the relationship between photon absorption and electron flow. Look for panels with exposed terminals rather than pre-wired connections, so students can practice circuit building rather than just plugging things in. Check the link below to see the current price for a good example. The main drawback is that cheaper panels often come with no documentation about their actual max current output, which makes calculating power frustratingly imprecise. DC hobby motors rated for 1.5 to 3 volts serve double duty as both energy consumers when you're powering them with solar panels and energy generators when you spin them manually or with wind to create voltage. This beautifully demonstrates energy conversion reversibility. Choose motors with exposed shafts so students can attach fan blades, wheels, or pulleys. Generic 130 size hobby motors from electronics suppliers work perfectly and cost pennies. They're disappointingly fragile, though. The tiny brushes wear out quickly with repeated experiments. Wind turbine blade sets or lightweight propeller assortments convert wind energy into rotational mechanical energy, and blade design becomes the experimental variable. Students can test 2-blade versus 3-blade configurations, blade pitch angles, and surface area. Craft foam sheets or balsa wood let students fabricate custom blades, which adds a design engineering dimension. Pre-made blade sets save time but remove the iterative design process that builds the deepest understanding. Hand-crank generators or dynamo units let students feel the resistance of energy generation in their own muscles, creating a kinesthetic connection to the concept of mechanical work input. Check the link below for a kit that includes a small dynamo with a gear ratio that makes cranking manageable while still generating measurable voltage. The crank handle is awkwardly short for larger hands, making sustained cranking uncomfortable. For hydroelectric experiments, you need a wheel with angled cups or blades that can spin when water flows over or through it, coupled to a small generator. Many students build these from scratch using plastic spoons and cardboard, but a pre-made unit gives you reliable baseline performance data before moving to custom designs. Flow rate requirements are finicky. You often need a surprisingly large volume of water or a significant height drop to generate measurable voltage. Micro wind turbine kits with generator integration combine blades, a mounting system, and a small generator in one assembly, letting students focus on sighting and measurement rather than mechanical troubleshooting. The trade-off is reduced customization. You can't easily swap components to isolate variables. Look for kits that include multiple blade sets or adjustable pitch mechanisms. Low-voltage LED arrays in various colors serve as immediate visual feedback for energy generation. They light up when voltage crosses a threshold, and different colors have different forward voltage requirements, creating a natural experiment in energy threshold detection. Red LEDs light at around 1.8 volts, while blue and white need closer to 3 volts, so you can demonstrate power output differences visibly. Buy assortments of 3mm or 5mm LEDs rather than pre-wired modules. Bare components teach circuit fundamentals. Small rechargeable battery packs, like AA or AAA NiMH cells, let students store generated energy and measure charging rates, introducing energy storage as a distinct engineering challenge from generation. NiMH batteries are safer and more forgiving than lithium-ion for student experimentation, and you can use inexpensive USB-based NiMH chargers with multimeters to track charging current. The downside is that charging is slow. Students often need to wait hours or days to see meaningful charge accumulation, which disrupts the immediate feedback loop. Now let's talk about measurement and data collection tools. Without measurement, you've got a demonstration, not an experiment. This is where supply shift from "look, it spins" to genuine scientific inquiry that aligns with rigorous educational standards around data analysis and computational thinking. A digital multimeter with voltage, current, and resistance modes is your non-negotiable centerpiece measurement tool. Students need to measure open circuit voltage, short circuit current, and resistance values to calculate power output and efficiency. Choose a multimeter with large, clear digits and a manual range selection option. Auto-ranging meters are convenient but hide the concept of measurement scale from students. Basic models around the $15 to $20 range work fine. Check the link below for one that offers good accuracy for the price, though the test lead jacks are slightly loose and require careful insertion. USB power meters, or inline current and voltage monitors, sit between a power source and load, like a USB-charged device, and display real-time voltage, current, power, and accumulated energy. They're perfect for renewable energy experiments because students can watch power fluctuate as sun intensity changes or wind speed varies. The limitation is that they only work with USB-compatible voltages, roughly 5 volts, so you'll need DC to DC boost converters for lower voltage solar panels. While digital meters are more precise, analog voltmeters or ammeters with moving needles give students a visceral sense of fluctuating power. The needle bounces and swings as clouds pass or wind gusts hit, which builds intuition about renewable energy variability that static digital numbers don't convey. Educational supply versions with large wall-mounted displays work well for group demonstrations. For solar experiments, light intensity is your critical independent variable, and eyeballing bright versus dim doesn't cut it for rigorous work. Lux meters quantify illumination, letting students correlate light levels with voltage output and calculate panel efficiency. Smartphone apps with decent accuracy are available if you search for Lux meter in app stores, but dedicated handheld meters respond faster and work better in bright outdoor conditions where phone screens wash out. To investigate wind turbine performance, you need an anemometer to measure wind speed in meters per second or miles per hour, then correlate that with power output. Handheld cup anemometers or digital vane anemometers both work. Look for models that average wind speed over time rather than just showing instantaneous readings, since wind speed fluctuates wildly. Even inexpensive models drift out of calibration, so treat absolute values skeptically and focus on relative comparisons. Temperature becomes relevant when students investigate panel efficiency degradation at high temperatures or measure energy loss as heat in motors and generators. Non-contact infrared thermometers are faster and safer, but they measure surface temperature only. Thermocouple probes give you internal readings. Either way, temperature data adds a dimension to efficiency calculations that surprises most students. They don't expect solar panels to perform worse when they're hot. Energy is power multiplied by time, so you need precise time measurement to calculate work done, charging rates, or how long a stored energy reserve can power a load. Smartphones work fine, but dedicated stopwatches with lap memory let students capture multiple intervals without resetting. Laboratory timers with large displays help when you're working with a group. For experiments involving potential energy conversion, like water wheels or gravity-powered generators, you'll need to measure mass to calculate gravitational potential energy. A basic kitchen scale works for most experiments, but if students are building miniature turbines with different blade materials, a 0.1 gram resolution scale helps compare component weights meaningfully. Moving on to electrical connection and circuit building supplies, this is where I see the most frustration in home experiments. Families buy great core components but skimp on connection materials, then waste hours troubleshooting loose wires and intermittent contacts. Professional setups include robust reconfigurable connection systems. Breadboards, specifically standard 830-point solderless versions, let students build and modify circuits without soldering, which is essential for iterative experimentation. Check the link below for a kit that includes a breadboard, jumper wires, and a power supply module. Internal contact strips lose tension with heavy use, causing intermittent connections, so buy a few spares and rotate them out when you notice flaky behavior. Alligator clip test leads give you quick reconfigurable connections to solar panels, motors, battery terminals, and multimeter probes. Buy sets with shrouded metal clips. Bare clips are a short circuit waiting to happen when they touch each other or nearby conductors. The clips wear out and lose grip strength, so you'll replace these regularly. You need both solid core jumper wire for breadboards and stranded wire for external connections. Solid core, usually 22 AWG, works for breadboard insertion. Flexible stranded wire connects to components with screw terminals or solder joints. Pre-cut, pre-stripped jumper sets save time. Bulk wire spools give you custom lengths, but require a wire stripper. Color code your wiring, red for positive, black for ground, other colors for signal paths to make troubleshooting easier. When you're connecting multiple components to a single power source, like parallel solar panels or series battery packs, screw terminal blocks or barrier strips give you secure, labeled connection points. They're especially valuable for semi-permanent setups that students will return to over multiple experiment sessions. Cheap terminal blocks have soft brass terminals that strip easily, so look for ones rated for at least 10 amps, even if your experiment draws milliamps. For any soldered connections or exposed wire junctions, heat shrink tubing provides insulation and strain relief. Buy an assortment of diameters. You'll use 3mm and 5mm sizes most often. A heat gun or even a lighter used carefully shrinks the tubing. This feels like a minor detail until a student shorts out a circuit because bare wire touched a metal workbench. Electrical tape is the backup for everything. Use it to secure loose connections, label wires, insulate terminals, and provide strain relief. Real electrical tape, the vinyl kind rated for electrical use, is self-extinguishing and stretches. Generic tape dries out and leaves residue. Black is standard, but multicolor sets help with circuit tracing. You'll strip dozens of wire ends during a single experiment session, so wire strippers matter. Adjustable wire strippers let you dial in the exact wire gauge. Multi-notch strippers have sized holes for common gauges. Either works, but avoid cheap strippers that nick the conductor strands. Damaged wire breaks easily. Once students finalize a design, soldering creates reliable, low-resistance connections that won't wiggle loose. A basic 30 to 40 watt soldering iron works for electronics. Lead-free solder is safer but requires slightly higher temperatures. Soldering introduces a new skill domain, so budget time for practice joints before students work on actual components. This is where you're introducing industry-standard assembly practices used in actual renewable energy installations. Let's talk about data recording, analysis, and presentation materials. The difference between a science activity and a science experiment is the systematic collection and analysis of data. These supplies turn observations into evidence. An engineering notebook or bound lab journal is essential. Loose papers get lost, and spiral notebooks let pages fall out. A bound composition notebook with numbered pages and a table of contents becomes an authentic engineering documentation tool. Students should record hypotheses, procedure steps, raw data tables, observations, and post-experiment analysis all in one place. I tell students this is the same type of documentation engineers keep in industry. It's legally admissible proof of who discovered or invented something when. For plotting voltage versus current curves to find maximum power point, power output versus wind speed, or efficiency versus light intensity, students need proper grid paper. Quarter-inch or 5 mm grids work well. Logarithmic paper is useful for advanced students investigating exponential relationships. Alternatively, students can use spreadsheet software, but hand plotting builds deeper understanding of scale, axis labeling, and data distribution. For experiments generating lots of data points, manual calculation becomes tedious and error-prone. Spreadsheets let students create formulas once, then apply them to entire columns. They're also where students learn to create proper graphs with labeled axes, units, trend lines, and error bars. Google Sheets has the advantage of real-time collaboration if multiple students are working together. This connects directly to data analysis skills used in professional renewable energy system design. Visual documentation captures experimental setups, component arrangements, and results displays. Photos are essential for science fair presentations and engineering reports. Students should photograph their setup from multiple angles, include a ruler or reference object for scale, and capture close-ups of critical connections. Teach them to export photos with timestamps. It's a basic evidence practice. Eventually, experimental findings need to be communicated. Physical poster boards work for traditional science fairs. Digital slides, PowerPoint, Google Slides, or Keynote suit classroom presentations or virtual sharing. The key is teaching students to organize content logically. Question, hypothesis, methods, data, analysis, conclusion. It's the same structure they'll use in any technical field. Clear labeling prevents confusion when you've got multiple circuits, component bins, or battery packs in play. Labels on storage containers, experimental setups, and even individual wires make setup faster and reduce errors. Even masking tape and a permanent marker work if you don't have a dedicated label maker. Power calculations, efficiency percentages, and uncertainty propagation require more than basic arithmetic. Students need square roots for RMS calculations, exponents for area calculations, and possibly trig functions if they're optimizing solar panel angles based on latitude and season. Graphing calculators are overkill unless students are already using them for math coursework. Smartphone calculator apps work, but create distraction risk. Now let's cover supporting infrastructure and safety equipment. These are the supplies that don't generate or measure energy, but make experiments possible, safe, and repeatable. This is the infrastructure that separates a one-time demonstration from a sustainable learning environment. For indoor solar panel testing, you need a consistent, repositionable light source. An adjustable desk lamp with a flexible arm and bright LED bulb works well. A 60-watt equivalent LED bulb in a gooseneck desk lamp gives you reasonable intensity and flexibility to test distance and angle variables. The lamp needs a stable base. Cheap plastic lamps tip over easily. Recognize that even bright indoor lighting is much dimmer than outdoor sunlight, so results will differ significantly. You can also look at our guide on how to measure solar panel efficiency in science projects for protocols around light source standardization. For wind turbine testing, when outdoor wind is unavailable or inconsistent, an electric fan with adjustable speed and a stable base provides controlled airflow. You're trading realism for experimental control. Real wind gusts and shifts direction. Fan wind is steady and unidirectional. Measure distance from fan to turbine carefully. Wind speed drops off quickly with distance and also varies across the fan's diameter. Hydroelectric experiments need flowing water, which means either a faucet, which is variable flow but wasteful, a raised reservoir with a valve, which is adjustable and reusable, or a recirculating pump setup, which is complex but sustainable. The elevated reservoir approach works best for most families. A 5-gallon bucket elevated 3 to 6 feet with a plastic spigot valve gives you adjustable flow and measurable head height. Renewable energy experiments involve multiple components with connecting wires, and everything needs to stay put when you're adjusting variables or taking measurements. A foam core board, plywood sheet, or plastic project tray gives you a stable work surface you can move without disturbing the setup. Include mounting options like Velcro strips, hot glue, or even just masking tape to secure components. Solar panels, terminal blocks, and many hobby motors have small screw terminals that require number 0 or number 1 size screwdrivers. A basic precision screwdriver set costs a few dollars and prevents stripped screws and frustrated students. Magnetic tips are helpful but not essential. Anytime students are soldering, cutting wire, or working with springs and spinning components, eye protection is non-negotiable. Splashing water from hydroelectric setups is usually harmless, but solder splatter or a snapped wire under tension can cause serious eye injury. Buy safety glasses that fit properly and aren't so uncomfortable that students take them off. Once you've got 5 wires running from a solar panel array to a breadboard circuit to a multimeter to a load, cable management stops being optional. Organize and secure cables so they don't pull on delicate connections or create trip hazards. Reusable hook and loop straps are better for experimental setups than zip ties, which need to be cut off when you reconfigure. Small components like LEDs, resistors, wire ends, screws, and blade sets disappear quickly without organized storage. Tackle boxes, craft organizer cases, or compartmented plastic bins keep everything findable. Label each compartment. Transparent lids let you see contents at a glance. While the goal is renewable energy generation, you'll often need a known, stable power source for control comparisons or to power measurement devices. A variable DC power supply is ideal, but expensive. AA battery holders with fresh batteries work fine for most experiments. This gives students a baseline. The solar panel generates 2.5 volts compared to 3 volts from 2 AA batteries. Soldering irons, hot glue guns, lamps, fans, and other experiment infrastructure all need power. A surge-protected power strip prevents equipment damage, and a long extension cord gives you flexibility to work near windows for solar access or sinks for hydroelectric setups. Make sure cords are rated for the total amperage you're drawing. If you're soldering or using hot glue guns, fire safety equipment needs to be within arm's reach. A small ABC-rated fire extinguisher handles electrical and common combustible fires. A fire blanket smothers small fires without making a mess. Teach students to turn off heat sources immediately if something starts smoking, and never leave heated tools unattended. Before you start your renewable energy science experiment, run through this quick verification to make sure you have the essential supplies and infrastructure in place. You need at least one energy generation component, like a solar panel, wind turbine, or hand crank generator with documented voltage and current specs. Multiple energy loads like LEDs, small motors, or buzzers with known power requirements. A digital multimeter with fresh battery and working test leads, a breadboard with assorted connection materials like jumper wires and alligator clips, measurement tools appropriate to your experiment type such as a lux meter for solar or anemometer for wind, a bound lab notebook or structured data recording system, calculation tools like a calculator or spreadsheet software access, appropriate environmental controls like an adjustable lamp for indoor solar or a fan for wind simulation, safety equipment including eye protection, a clear workspace, and fire safety tools if using heat, a stable work surface with secured components and organized cables, a storage and organization system for small components, and a photo documentation method, either a camera or phone, for recording setups and results. Let's address some frequently asked questions. What renewable energy science experiment supplies do you need to get started on a basic solar power project? You need a small photovoltaic solar panel in the 1 to 6 volt range with exposed terminals, a digital multimeter to measure voltage and current, a breadboard with jumper wires for circuit building, several LEDs of different colors as loads, and a bright adjustable desk lamp for indoor testing or access to direct sunlight for outdoor experiments, plus a notebook for recording your measurements and observations systematically. You can use some household items instead of specialized renewable energy science experiment supplies, but you'll still need specialized components like solar panels, small motor generators, and multimeters because these aren't common household items, and the specific electrical characteristics matter for meaningful data collection. An approximate voltage isn't sufficient when you're calculating efficiency or power output. A complete starter set, including a solar panel, small motor generator, basic multimeter, breadboard, connection supplies, measurement tools, and documentation materials, typically costs between $60 and $120, depending on whether you choose individual components or educational kits. More advanced experiments involving multiple energy sources or data logging equipment run $150 to $250, which represents a worthwhile investment in reusable tools your student will use across multiple projects as they advance their skills. The key is choosing supplies that expose rather than hide the underlying physics, that allow manipulation of meaningful variables, and that support rigorous measurement instead of just subjective observation. When you invest in quality measurement tools, flexible connection systems, and proper documentation materials alongside your energy generation components, you're building not just one experiment, but a complete renewable energy learning laboratory that will support increasingly sophisticated investigations as your students' skills grow. That progression from hands-on exploration through data-driven analysis to engineering-level problem-solving, that's where genuine STEM competency develops, and it starts with having the right supplies organized and ready to support curiosity the moment it strikes. That's it for this episode of the STEM Lab podcast. Thanks for listening all the way through. We've got new episodes dropping every Monday, Wednesday, and Friday, so you won't have to wait long for the next one. If you found this episode helpful, I'd be incredibly grateful if you'd leave us a 5-star rating and write a quick review. It genuinely makes a difference in helping other parents and educators find the show when they're searching for this kind of content. And if you haven't already, hit subscribe or follow so you get notified the second a new episode goes live. I'll talk to you again soon.